Cool. Yeah, thank you for a great talk, Boya. And then also thank you for hosting us, Foxo 51. Thank you, Jimmy. Yeah, so here I'm Shuri. I'm here representing CMU, and here with me are Omar, and also Diaya Tony. And here we're presenting our work on Map It Anywhere, which is empowering bird's eye view mapping with large-scale public data. And this is really related to Foxo 51, really amazing like data creation engine. And we're also trying to build the same like leveraging. How can we best leverage disparate sources of data, find our own way to create it in order to empower something that we cannot achieve before? So I want to start by introducing our problem, which is, so here we have a very canonical view. This is actually taken just out in Pittsburgh, where I'm driving. So when navigating, there is often a lot of the world is unobserved. So there might be views that are blocked by cars on the left, or maybe also views that are blocked by plants at the right. So humans actually navigate this unknown space really intelligently. So let's take it more under the brain, I guess, on how we think about the world. And a lot of times we are thinking a top-down Cartesian layout of the world, which we refer here to bird's eye view layout, so BEV. And we have a mental picture of how the world is generally structured, and therefore we are able to estimate, okay, this is like from a top-down perspective, this is how the intersection crossing looks like. In orange is like where the sidewalks will be and also where the buildings are. And this is really important because we are also reasoning beyond block views. And this really lets us make good navigation decisions when we're driving, when we're also walking. So for example, here, maybe our goal is to go to the right. In this bird's eye view layout, robots and human alike can really natively be able to plan a good path. So why don't we just use OpenStreetMap, which is a very powerful data source that I'll talk about later, plus GPS. Just run that on a robot online. And a big problem is because of that, especially in urban canyons, due to occlusions, we get poor GPS positioning because they can't really do a triangulation well, such that potentially you're actually at an intersection, but the estimated GPS position may be super far out inside a building. And these are rendered an actionable map. So this really begs the need for online map prediction, which here is the problem of, given a first-person view image, how can we output a predicted top-down bird's eye view map, semantic map, so that ground robots can use it? So here's a quick teaser of our work, Map It Anywhere, which is a data engine and a baseline model to power generalizable bird's eye view mapping. And the key innovation is on the data curation pipeline. So here we present a MIA data engine to curate from disparate crowdsourced platforms to create an incredible amount of data, which then leads us to training a simple map prediction model that actually works quite well in the wild. And here are some other self-collected videos all over the US and even Zurich at night. So stepping back to the challenge, a key challenge is the generalizability of bird's eye view map prediction models are limited by the small regions captured by current data sets. So for example, Newseeds is a very powerful, popular map prediction data set, however, only covers small regions of just 2 cities, and similar with Kitty. And so how can we imbue robots with the ability to predict maps and go anywhere? Specifically, how can we develop an ecosystem for bird's eye view mapping foundation models? And there are 3 key ingredients to solving this. First, we need to solve the data set issue, where current data sets, while powerful, is insufficient for the generalizability needed, where it is limited in geographic diversity and also in like the different types of camera model at test time. In the model, we need to develop a model that, again, can work well for arbitrary cameras. And finally, the evaluation piece is critical. how can we create a benchmark for anywhere mapping that is challenging and long-lasting so that we can guide the community towards important problems? And in order to empower all three questions, our key insight is to curate from large-scale crowdsourced platforms, which really changes the paradigm from us waiting for autonomous driving data to be released to actually we postulate that the data for what we need is already out there, just in these forms of two disparate crowdsourced platforms. Specifically, first-person view we can gain from Mapillary, and then we can associate it using like their location to OpenStreetMap, which is a incredible crowdsourced platform for semantic map. And we were really inspired by great work on internet that showcases the potential of using these two data sources to enable generalization for a related map task. And our question is, how can we use them for map prediction?
So using data from crowdsourced platforms unlocks unprecedented worldwide diverse data. And this is really what pushed us towards using these crowdsourced platforms. As we can see on the left side, the FPV image locations available in the current map prediction datasets are all very geographically limited. And this really hinders the ability of any model out there, no matter how good, to be able to generalize to out of distribution or other locations. Whereas data included in Mapillary covers almost the whole world, spanning all of the continents. And it's a really a large source of FPV images that we can leverage. And apart from the geographical diversity in Mapillary, which is, we think, key for generalizable map prediction, there are also a variety of camera types available. So most of the existing data sets, they usually have a single sensory setup where they collect all of their data. However, with crowdsourced data, you really get the camera diversity that is needed to really generalize. However, we cannot really directly use the crowdsourced data because it has a couple of flaws. So, for example, with OpenStreetMap, they rendered the OpenStreetMaps, and here we see the rasterized or rendered maps. And we really see a disparity here between, or a misalignment between the rasterized map, the rendered map, and the satellite imagery. And this disparity would really affect map prediction tasks, because you need the FPV, the key elements, the key structures in the FPV to align well with the rendered or your semantic map. So we see on the right, for example, on OpenStreetMap, road widths are represented as single pixel lines, which is not aligned with the satellite. There's no sidewalk information, which is critical for applications like autonomous wheelchairs. There's also too much information, sometimes unrelated to the navigation task, like just a random tree on the right park. So we really need to be able to generate a rendered map that is actionable and that aligns well with satellite imagery, such that it aligns well with the FPV. And this is where MIA comes in. So in MIA, we developed a rendering pipeline. So rendering is just simply converting the vectorized format into an image format. And here we've carefully compared with the satellite imagery across different cities and tuned our rasterization pipeline to match the satellite. And as we can see, also the sidewalks are shown correctly. And we can even we're even able to reason about one-sided sidewalks. So we see here in the FPV, for example, on the left side, there is a sidewalk. However, on the right side, there is none. And we see that reflected correctly in the MIA rasterized map. And apart from being able to carefully rasterize a map, we need to be able to also filter and select good FPV images. So for example, we see here that this is a data sample from Mapillary. We see that the estimated pose that Mapillary is showing has some error. However, the actual pose should be somewhere in this area. So we develop a filter that acts like a proxy for the pose calculation accuracy. So we basically calculate the discrepancy between the registered location, so the location that is estimated by the actual GPS sensor on the robot or on the vehicle, and the estimated location or the pose from SFM, structure from motion estimation, which really utilizes multiple sequences of images and is able to, in many cases, to register the FPV image more accurately. And we postulate that if this discrepancy was big, then the actual pose is unreliable, and we would not, for example, use it in our data set. And we also use other filters. There's a camera model filter that we use to simply select the cameras that usually produce good pose estimation. There's a recency filter, and there's other filters, and they're all very easily customizable to navigate or to select the thresholds. And they can, you can take out filters, you can add filters depending on your specific needs. So this is the MIA data engine. It automatically curates FPV BEV pairs worldwide. And we really emphasized this a simple user interface that really hides the complexities of the whole pipeline. So by simply typing in a list of cities, you immediately get access to this huge pool of 2 billion plus images in Mapillary, and this huge database of OpenStreetMap, where 83% of the global roads have been mapped. And just by selecting these cities, the pipeline goes, it will automatically fetch the boundaries for you, fetch the images available, filters them, gets the FPV, undistorts it, and then goes all the way through OSM as well to generate the final semantic masks. And to really test or stress test the power of our MIA data engine, we sampled, we would say, a small subset of what it can provide, which we call MIA dataset V1. And this dataset has right now 1.2 million FPV BEV pairs. It covers 6 times more area than the closest public dataset. It covers 6 different cities. And as you can see, the diversity here is really great. And again, diversity is we would say, critical to a generalizable map prediction system. We can see in terms of time of day, the FPV images span all times of days, vehicle domain, you have tunnels on the highway, urban, rural, season, weather, even pedestrian domain. You have people walking in a park, in a forest, in an alleyway. So, and this is again, the amount of diversity that we've seen with dataset is really interesting. And this is a table from our paper, just highlighting these attributes in a summarized format and comparing it with the other available public datasets. We can see, for example, that in terms of area covered, we're at 470 kilometers. We have 1.2 million. Number of camera models is significantly higher. the domain types and camera platforms, whether it's the capturing platform, whether it's by car, bike, or pedestrian, is all available. And the nice thing is this is all automatically curated. No human was, filtering out images, and you can really tap into this potential by just inputting a list of cities. And that's I'll hand it to you.
All right. Hey, this is Tony, and I'm going to introduce our model, which is called Mapper. So with this amount of data in its rich diversity and in different settings, our assumption is that training a simple map prediction model, we will be able to outperform the current state of the art. So as you can see, here's our pipeline. With our FPV image, we first generate its feature embedding FPV feature image from the dyno encoder, and then we use another scale estimation model to use this feature map to generate the scale, the pixel scale for each of the pixels. And then with the pixel scale and the FPV feature map, we can then do a 3D lifting and then flatten the feature map into the BEV space, so which is the top-down space. So in the end, we use a really simple map prediction model, which is just a UNet, and then we will be able to generate our predicted semantic map. So here's our first research question. Most models are developed to use only one dataset and one camera, or like using one dataset and multiple cameras. So here's our challenge. In our dataset, we have many cameras with vastly different focal lengths. As you can see on the images here, we have different resolutions, different width and heights, different focal lengths as well. So the question is, how do we build a map prediction model that's generalizable to different camera models, different images? So here's our solution. We use a front end that predicts scales that can then be mapped to depth using known focal lengths. So specifically, it's our scale estimation model. We first estimate each of the pixels into one of the 32 scale bins, and then we use then we can generate then we take the log scale of it, so such that we will be able to get a depth in our polar array. So this is our polar projection, and then followed by the polar projection, we have a Cartesian projection, such that with this FPV feature map, we'll be able to generate a BEV feature map. So this allows easy usage of different camera models since we can give it the camera parameters. And then in the end, as I just introduced, we predict a final map from BEV features using a really simple model, which is a UNet. So it shows that MIA enables map prediction model to go more anywhere out of the box. So here's our first visualization of our model prediction. So on the top column is the first column is the ground truth. The second column is our mapper prediction. And the third and fourth are the current state-of-the-art models that are trained on conventional datasets, for example, Newsings and Kitty. So if you look at the visualizations, mapper predicts maps more similar to ground truth. Like we can get rather straight road. It knows where the sidewalk is, and then it can also infer the buildings on the right. But for Tame and Sky Eye, they can do relatively well on road. But when it comes to the categories like sidewalk and crossings or buildings or terrains, it might get confused because of such images are so out of distribution compared to Newsings and Kitty dataset. So here's more results on MIA images from untrained cities, which is called MIA OOD out of distribution, where such images are not trained, such cities are not trained in our mapper model. So you can see that the inference result is that mapper can still do well in most of the classes, like road, sidewalks, and also building. But for Tame and Sky Eye, they can do well on road, but then for some of the images that are in low lighting, in bad weathers, it shows it might get confused on roads, and maybe at the image on the bottom right, it's kind of confused. So this visualization shows that MIA enables our map prediction to predict other cities that our model has never seen before, or other camera models. So this is our results table from our paper. With this statistics, we can see that MIA's zero-shot performance generally exceeds state-of-the-art baselines across multiple data sets. So here, zero-shot means that the comparison is, for example, for table A, zero-shot Newsings is that we inference mapper trained on MIA dataset on Newsings dataset, and then compare to TIM model that's trained on Newsings dataset, inferencing on Newsings dataset. So we can see that Mapper model compared to SkyEye that, both of them has never seen using this before, Mapper can do it really good. And also the same thing also holds for Kitty 360 BEV. And so when it comes to zero-shot MIA OOD, the Mapper model that has never seen this subset of our dataset can still do really good well. That's comparable to Mapper plus OOD model. And then this is our final evaluation study. So we try to fine-tune Mapper on Newsyn's dataset, maybe just a partial of Newsyn's dataset, or 100% of Newsyn's dataset. So on the first row is Mapper with 0% of Newsyn's. So we have not yet fine-tuned Mapper. We can already get a really good results from it, as you can see. And then with just 1% of fine-tuning on Newsyn's dataset, we already get a 33% boost on our performance. And then when 1% comes to 10%, the performance, like the drivable areas and main region areas, is even comparable to TIM trained on 100% of Newsyn's dataset. So this draws to another conclusion that pre-training on MIA enables effective fine-tuning with limited data. And now here are some more results on self-collected videos. As you can see, on the top left, that's Pittsburgh, and Seattle and Zurich. So you can see that our model for each of the frame that generates really straight roads, and also it knows where the sidewalk is, and it can see the buildings. So which shows that Mapper can even see videos that are captured using our own phone cameras or other different cameras. So yeah, this is for a Mapper model, and I'm sure he's gonna take over.
Yeah, thanks. And so kind of like the last question that we're interested in is on evaluation, where we're really thinking about how that MIA data engine can empower an ever-growing data set for training and evaluation. So now, since our paper, we have also been extracting data beyond US cities, for example, from Europe, Asia, and also Australia. We have also extracted a rural data set, which really actually stress tests a lot of the current approaches where it really does not do well, including our own. And hopefully that these data sets will really guide future work on how can we achieve anywhere map prediction. So on to the next steps, we're really hoping to build out a foundational ecosystem for multimodal mapping that we have already leveraged OpenStreetMap and Mapillary, and we're exploring how can we add satellite imagery and also embodied robot data sets to really create a better foundation data set and evaluation for multimodal mapping. Cool. So in summary, we present Map It Anywhere, MIA, which is a data engine for generalizable bird's eye view mapping. And the key insight is we twist how we conventionally get map prediction data from waiting to collect for AV companies to collect more information to creating what is already out there for our need. And while we have a 6 times larger data set than conventional data sets, this is, I emphasize, just a sample of what we can already get. And unlocking such unprecedented diversity has really led to more generalizable performance. And to summarize, I really want us to take away this generalizable insight that we executed in MIA is if you're working on a machine learning problem where data scarcity is the problem, really try to think of creative automated ways that you can collect the data set, potentially by combining different data sources for your needs, and then use that to build a data engine. So yeah, thank you. And we also actually have some demos prepared if we have time for that.
I think we may have time for those, but why don't we tackle a few questions that came in. Mike asked this question, and I think it came around slide number 15. How do you rasterize? Is it vector-based? Can you tell more about how you do it?
Yeah, so for the rasterization, we really took advantage of the map machine framework. We had to modify it a little bit such that it infers sidewalks correctly, and we had to tune a lot of like the styles and the default numbers that they were using.
This next question came in around slide 18. So you did already talk a little bit about the data set, but I guess a more generalized question was, how does the data set compare to Google Street Maps?
Yeah, definitely. So the semantic map data source is from OpenStreetMap, and I think Google Street Map that we've seen is generally has less data noise because it is not a it is a proprietary data source, whereas OpenStreetMap is actually a crowdsourced platform and therefore is open. So generally we see that there is actionable data from OpenStreetMap, which is what we leverage. However, there definitely do exist data noise, which are some interesting next steps that we can do. However, I would highlight that it would be difficult to directly use Google Street Map without their proprietary license, whereas the methods that we're using is much more commercial friendly.
Next question, has Mia been tested for real-time applications? Do you know what the performance bottlenecks are in the model?
Yeah, so we are beginning to test things on like a real robot, and generally the runtime is actually quite fast, especially because we are leveraging like small map prediction models. So generally, I think we get around 5 to 10 hertz. So it's actually quite real time.
Next question, do you think that the zero-shot prediction performance of your model will be even better when you use multiple frames instead of one, like a stereo pair or a future frame?
Yeah, that's a great question. Definitely. I think, and this also has been shown in previous papers, which is like the conventional data set using multiple frames. We're really excited to, while we have been focusing on single frame to really test the insight, we think our pipeline is amenable to doing multiple frames, and then we can augment our model to do that. And I really believe, I think critically, I think it can help with like the temporal consistency of the prediction and also just better accuracy in general.